My name is Christy Martino, and I'm an applications engineer at Modelithics. And let's just start by talking about today's agenda. So today we're going to discuss S-parametre data files, which is our common representation of modeling components with RF microwave simulation software. And then from there, we'll transition into Modelithics scalable circuit models known as microwave global models and see how they can be a great benefit to design engineers. We'll also talk about nonlinear models and 3D EM models. And then Andy will show some demonstrations in Cadence AWR using Modelithics models. So let's proceed. So let's talk about S-parametre data files. These are a widely used representation for passive components in the RF microwave industry. These are essentially linear behavior models that are easy to use with any simulator. And these are determined from measurements that the manufacturer performed. However, these models do have a limitation, and that is an S-parametre data file only represents data when using one particular substrate or test fixture environment. However, as a designer, you might be using a different substrate or a different test fixture, so the results that you'll see may not necessarily agree with what's in that S-parametre data file. Now let's talk about Modelithics' unique microwave global models. These are scalable models that are based on actual measurements that were performed by Modelithics. Specifically, these models scale with respect to part values, substrates, and solder pad dimensions. So let's talk about part values. A single microwave global model typically covers the full range of part values for the part series that it represents. And because of that, that makes these models well suited for tuning and optimization. In addition, these models are also well suited for EM circuit co-simulations. And what's also useful about these models is that they include a parameter that allows you to de-embed the solder pads so that you can simulate the pads in the EM simulator. So for example, let's say you want to perform an EM circuit co-simulation with the Axiom simulator. You could use the sim mode parameter within the model and then set that to sim mode 2, which is the parameter to de-embed the solder pads. And then you will simulate the pads within the Axiom simulator rather than within the model itself. So these models include a number of useful features, and that's one of them. So let's talk about a simple simulation example to demonstrate part value scalability. So this is a model for a capacitor series from Passive Plus. And here we have this set up in a 2-port series configuration. And in this case, what we'll do is we'll simulate across 4 different capacitance values, 0.3, 1.2, 5.1, and 36 picofarads. And here are the results of that simulation. We have S11 on the right and we have S11 on the left and S21 on the right. And you can see how the model scales appropriately with respect to the capacitance values. So each graph shows the results for those 4 different capacitance values. And we see how the performance of the model changes appropriately. So again, this is very useful because it allows these models to be well suited for tuning and optimization. Now let's talk about substrate scalability. Here we have a model for a Johansen capacitor. Again, this is set up in a 2-port series configuration. And just to explain this a little bit more, substrate scalability is very important because the performance of these components does depend on the substrate that it's mounted on. These models allow you to enter your substrate parameters, for whatever design, whatever substrate you're using for your design, you would enter the substrate parameters and then the model will scale appropriately. So again, that's another important advantage of these models. So let's demonstrate that by running this simulation. In this case, we'll simulate this model across various substrate heights ranging from 10 to 55 mils, and we'll leave the dielectric constant at a fixed value of 3.5. So here are the results. On the left, again, we have the simulated S11, and on the right, we have the simulated S21. And we're showing the results for all the different substrate height values. So again, you see how the performance does change with respect to the height of the substrate. So this is very important because it shows you how the performance does depend on the substrate that you're using. Now let's also talk about additional models that Modelithics offers. Modelithics offers more than just models for RLC components. Also offered are nonlinear diode models. So models are offered for various Schottky, pin, and varactor diodes. And these diodes are from manufacturers like MACOM, Infineon, Skyworks, and more. And these models also include various features like bias dependence, temperature dependence, and also substrate scalability, like we just spoke about. So if we look at the top right, we're showing a model for a Skyworks SMV 2204-040LF varactor diode. And what you see here was taken from the model data sheet, this model features box. So in this case, the model is validated from DC to 20 gigahertz. And the measurement validations include DC-IV, multi-bias S-parameters, capacitance versus voltage, and resistance versus voltage. If you look on the bottom, you'll see the modeled and measured capacitance versus bias voltage. And it's showing you on the left, and on the right, it's showing you the S11 versus the bias voltage. So if you look on the graph on the left, where it's showing the effective capacitance for bias voltages ranging from -20 to 0 volts. And you see how the capacitance varies accordingly. And then on the right, we're showing S11 for bias voltages ranging from -20 to 0 volts. And again, you see how the S11 changes as we vary the bias voltage. Let's also talk about substrate scalability. These diode models are also substrate scalable. So for example, we're showing that same varactor diode on the left, and on the right, we're showing S11 data for 3 different substrates. So the red trace corresponds to a 6.6 mil thick Rogers 4350B substrate. The blue trace represents a 30 mil Rogers 4350B substrate, and the green trace corresponds to a 60 mil thick 4003C substrate. And in this case, the bias voltage is -2 volts. But you can see again how the performance changes as we vary the substrate. So again, that's a very important aspect, is that the performance does depend on the substrate that is mounted on. And these nonlinear diode models do capture that substrate scalability. Let's also talk about nonlinear transistor models. Modelithics offers nonlinear transistor models for various HAMT, MOSFET, BJT transistors, and more. And again, these models include features like substrate scalability, temperature dependence, bias dependence, and more. And these are well suited for power and noise analysis. So on the top right, we have this HMT MCL TAV 214LN model. This is a model for the mini circuits TAV2-14LN plus EP-HEM transistor. And again, this was taken from the model datasheet. You can see how the model is validated from DC to 20 gigahertz. And the measurement validations include temperature validations, DC-IV, multi-bias S-parameters, noise parameters, and then both single and two-tone power sweeps. On the bottom left, we have the measured and modeled S-parameters for 3 different substrates. Again, the red trace is 6.6 mil thick Rogers 4350B. The blue trace is 20 mil Rogers 4350B. And the green trace corresponds to 60 mil thick Rogers 4003C. And you see how the performance does vary depending on the substrate that you're using. And on the bottom right, we have the modeled and measured noise parameters of this transistor. So we have the minimum noise figure as well as the 50 ohm noise figure on the top left, and on the top right, we have gamma opt, and then we have the noise resistance on the bottom. And also, this model is validated for single and two-tone power sweeps. So we show these results on the bottom. On the bottom left, we have the modeled and measured single tone power sweep results at 10 gigahertz. On the right, we have the modeled and measured two-tone power sweep results at 10 gigahertz. Another important aspect of these models is that each model that Modelithics offers comes with its own model information data sheet. And this data sheet will give you all the information that you need to know about the model. You'll see information like the validated frequency range, how the model was developed. It'll talk about the different parameters, and it'll show you modeled and measured data for that particular model. So these model data sheets are an important benefit of the Modelithics models, and these are offered with every model that Modelithics offers. And here's some of the graphs for this particular model. This is a model for a GaN transistor, and we see load pull validation results here on this page, and again, single tone power sweeps, and so on. Let's talk about some of the examples that we've created in the AWR design environment with the Modelithics models. And Andy will do some live demonstrations later, but we'll just give an introduction to these now. So here's a bandpass filter example that you can read about from application note 66, which you can download from the Modelithics website. This is a filter design using models for 0402 size components. And on the left, we have the schematic, and on the right, we have the actual filter. And when we look at the results, so what we see here on the left, we have the measured data shown by the dash traces, and then the simulated results with ideal models shown by the solid traces. And if you look at that graph, you see how the simulated results don't agree with the measured data. And that's because we are using insufficient models, so we're not able to accurately predict the real-life performance. The graph on the right compares the measured data with the simulated results when using Modelithics models for all components. And now you can see how the simulated results do agree with the measured data. And that's a result of using the Modelithics models within AWR to accurately predict the real-life performance. Here's another example that includes a varactor models. This is actually the same varactor diode that we spoke about earlier. And this is a tunable filter that you can read about in application note 85, which you can also download from the Modelithics website. On the left, we have the schematic, and on the right, we have a photo of the actual design. So this design example includes the Modelithics models for the varactor diodes, and also Modelithics models for all the inductors and capacitors that are included here. And again, same thing, we have the simulated results and the measured data right here on these two graphs. So again, the left shows the measured data, which are depicted by the dash traces, and then the simulated results with ideal models. And again, you see how the simulated results don't agree with the measured data, and that's because we're only using ideal models for the components. And just to clarify, we're showing the results for 3 different tuning voltages, 0, 6, and 16 volts. On the right, again, we have the measured data shown by the dash traces, and also the simulated results when using Modelithics models for all components. And these are shown by the solid traces. And now you see we do have good agreement between the simulated results and the measured data. And again, that's a result of using Modelithics models along with the the Cadence AWR design environment, and that allows us to accurately predict the real life performance. So Andy will show you this in a little more detail later, and he's also going to show you a diode detector example. So now let's talk about 3D EM models. These are now offered for the Cadence Clarity Simulator. So what's important about 3D models is they give the designer insight into coupling and component interactions. So let's say you have a design in which components are very close to one another. These 3D models allow you to accurately predict the performance of such a design because these models can capture any coupling and component interactions that may be present. So you can still accurately predict the real-life performance even when you have components that may be talking to each other due to close proximity. These models can still capture those effects. So let's talk a little bit more about these models. Modelithics is able to obtain the necessary information from the manufacturers under an NDA agreement, and that allows the company to develop these 3D models based on the material properties thanks to these NDA agreements. And that allows these 3D models to be developed. These models are encrypted models that, so that the manufacturer's IP can be protected. And then these models are then distributed so that engineers out there can use them in their simulator. And again, like I said, these models are now available for Cadence Clarity. So again, Modelithics has a lot of experience with EM simulation. So these models can be quickly developed. And also, again, like I mentioned before, these models are very useful for complex designs in which you have component to component and component to package interactions. Now let's just show you a simple example of how this all works. So if you look on the left, we have three different scenarios. We have three capacitors in a shunt configuration. And in one case, the capacitors are very close to one another. And then in the second case, we separated the capacitors by some distance. We call that the middle spacing scenario. And then in the third scenario, we separated the capacitors even more. So in this case, what we have are three 12 picofarad Johansen capacitors, and we're using a 16 mil thick Rogers 4003C substrate. If we look at the graph here, the graph on the left shows the measured data and the circuit simulation results. When we look at the circuit simulation results, we see how the results, which are shown by the solid traces, don't really agree with the measured data when the components are very close to one another. So if we look at the blue symbols, those represent the measured data. I'm sorry, if we look at the red symbols, those represent the measured data when the components are very close to one another. The red line, that corresponds to the simulated results. And we see how that simulation is not really doing a great job of predicting the real life performance. Now, if we look on the graph on the right, this shows the 3D simulation results along with the measured data. Again, the solid traces represent the simulation results, and the symbols represent the measured data. If we look at that red line, that red trace on the right, that corresponds to the simulation results when the components are very close to one another. And we see how that does agree with the measured data, which are shown by the red symbols. So the point of all this is to show how these 3D models can still accurately predict real-life performance, even when components are very close to one another. So that's a huge benefit of these 3D models. Let's talk about how Modelithics can accelerate your design success. They allow for reduced PC board spins, reduced circuit design iterations, improved schedules, and increased productivity. Also, it allows companies to maximize concept to product time. And with the Modelithics models, you get all these models in one vast collection. So Modelithics' flagship product is the Modelithics COMPLETE Library, and that will include all the models in one library. Also, these libraries are updated on a regular basis to keep up with the new EDA software versions. Let's talk about some more features of these models. We spoke about some of them. We spoke about the 3D models. Discrete optimization is another useful feature that allows the designer to adjust the component values to the optimal real-life manufacturer part values. You can actually read more about this in application note 66 that I had mentioned before, that explains the whole process of discrete optimization. Additional parameters include noise parameters, orientation and selectability for capacitor models, EM circuit co-simulations that we spoke about, and more. So temperature scalability is another parameter. And also some models include bond wire de-embedding and so forth. So these plug and play libraries are available for various Cadence EDA software tools, the AWR design environment, as well as the Clarity 3D solver that we spoke about. Also, the models are available for Cadence Spectra RF. And models are available from over 70 leading component suppliers, and the models in the library represent over 27,000 components. So here on this slide, you see some of the vendors that are represented within the Modelithics COMPLETE Library. I'm sure you'll recognize some of these names. We have components like Vishay, Mini Circuits, AVX, Passive Plus, Kemet, and so on. So all these vendors are represented within the Modelithics COMPLETE Library. And again, these models are offered for both passive and active devices, including the RLC components that we spoke about, diodes, transistors, as well as other components like amplifiers, attenuators, couplers, filters, and so on. So in summary, S-parametre files are useful, but they lack the scalability that the scalable circuit models offered. Scalable circuit models are a better solution for designs that give the designer flexibility and much more features that are not available with S-parametre data files. These scalable models also allow you to de-embed the solder pads so that they can be used in EM circuit co-simulations. And then the full-wave 3D EM models are very useful for scenarios in which coupling and interactions can come into play. So with that, I'll turn it over to Andy, and he'll take it over from here.
Thank you very much, Chris. Thank you, Zahi, for introducing us to the topic of more advanced models. Let me grab and share my screen. Chris, I have to ask you to stop sharing, please, if that's okay. Thank you. I should be able to share my screen now, and I hope that you should be able to see the screen that we continue with the slides. So thank you for bringing up the concept of advanced models, Chris. I was an ex-design engineer at Marconi many years ago, and one of the devices that I designed was a down converter. And in fact, that is my next slide. There are surface mount components here, a dielectric resonating puck. And the question was, is it possible to design this type of integrated block, an RF and microwave block, in this case running at 5 gigahertz, correct first time or right first time? I think very much so if you used accurate models similar to those of Modelithics libraries for all of the active and passive components. If you use some of the 3D models we've discussed for the connectors and the 3D puck elements, then yes, you can design this right first time. Now, although this is a Droid design, the Modelithic libraries work across various substrates, and they can apply to PCB, 3,5 exotic materials, gallium arsenide, gallium nitride, but also multi-layer laminates. And today, links into Virtuoso Studio RF, a product that Cadence will launch soon, later this summer, will also allow designers to work in the silicon space. Now, unfortunately, this design was done 20 years ago, long before Cadence tools, microwave office tools were available, all the Modelithics libraries. So it was not designed right first time. It took a good few iterations to get this correct, and cost and time, sadly. So what is microwave office? Just a quick bit of background on the microwave office and VSS tools from Cadence. What we're discussing is a design environment platform, and that platform ties together other simulation technologies all in one single database. That allows us to run circuit level simulation, as Chris has described, for filter design perhaps, but also concurrent layout. That layout is generated both from the models for transmission line elements, for example, but also the Modelithic libraries come with a full 2D and 3D package outline. And we can go straight to mass manufacture, be that GDS2, DXF, or Gerber, from that layout design. Our software and its brand, mmWave Office and VSS, is known for its ease of use and having speed and high accuracy associated with the simulators. And as Chris mentioned again, the ability to either dynamically tune these components from the library or to optimize critically across the parts that you can physically buy from the manufacturers, not ideal infinite decimal point numbers of capacitor or inductor values that you can't physically purchase. That makes it really difficult and incredibly hard to get a right first time design. So the most widely used product from the Cadence AWR family is mmWave Office, commonly used for the design of MICs, that's microwave integrated circuits, MMICs, monolithic microwave integrated circuits on exotic material, but primarily RF PCB boards and modules. You've seen one just a few moments ago on a slide a little earlier. The technology type is simply a process design kit or a PDK that we load on top of the software. And that's exactly how we load the Modelithics library into the tool. We do file new with library. I'll show you that in the software tool itself in a few more slides' time. Customers who use mmWave Office are looking to verify that the designs will work long before building them. We've mentioned the dynamic tuning and optimization, but also yield analysis. It's critical to have some spread of board material, perhaps, or thickness of your etching trace widths in order to get a realistic representation of what you might manufacture versus an ideal nominal simulation. We even have transient time domain capability inside the mmWave Office tool since the acquisition of AppLac, but primarily we're working in the linear and nonlinear frequency domain for microwave and RF circuit design. On the systems side, we can then take those circuit level designs, it may be the filter that Chris described, and drop that into a system simulation workbench. In there, we have all of the wireless communication standards, particularly for radar, for 5G, and other proprietary standards. But it's a system simulation tool that is impedance aware with the behavioral models. That means signals don't just evaporate if they don't make it through a filter, they get reflected and remixed further up the chain. So even at a systems level, we can take into account that layout and of course the models that Chris has described in terms of the physical footprints for components. You'll see in the top center of the picture on the right here, the capacitors are mounted horizontally. But in some cases, they may be mounted vertically to try to reduce the stray component capacitance. And of course, VSS can link into MATLAB and LabVIEW as one might expect for doing lower frequency baseband simulation. Now, in many instances, getting the component models correct is critical, but also the ever-increasing need to shrink designs and to make everything as miniature as possible, both to save on area, but also to save on physical size of the finished article, means that electromagnetics is becoming more and more important. With inside the Cadence AWR tools, Axiom gives us access to a planar 2D simulator. And that allows us to take any of the on-chip or on PCB board tracks, the passive interconnect across to a planar 3D electromagnetic world automatically. Axiom is an open boundary method of moment solver, and that means that we can also do antenna and beam steering calculations within that tool, and they become sub-circuits in the final design. We'll see in a moment the filter that Chris defined with the layout tracks taken through to the EM tool automatically, and any stray coupling that occurs between dissociated items then becomes part and parcel of the simulation design. And along with the electrical models from Modelithics, that makes our simulation results incredibly accurate, not just in terms of return loss, but also in insertion loss and loss through the copper track and its thickness. You'll see in a moment when I open the software how effortless it is to export that track layout into the EM tools, and we'll cover not just the stray effects from the components, but also any of the tracks that interact and couple, or perhaps even radiate. Now, in some cases, planar EM simulation is not quite sufficient. If you have a connector to board transition, that's really a 3D problem. So with inside the same tools, similar to Axiom, we have the ability to extract that design to Analyst. Analyst is a 3D FEM, finite element mesh EM solver, and that will solve Maxwell's equations in full 3D EM, looking at the volume of the problem. We would need to use that perhaps for waveguide or for bond wire transitions in packages that Chris described as a 3D package. Since the acquisition by Cadence have a tool that goes by the name Clarity, a very similar 3D FEM solver, but that was designed from the bottom up to work across parallel compute farms and parallel cores. And it far exceeds the simulation capacity of other competing products in terms of size of problem and speed of solution. And once again, EM extraction from that automated circuit level design and the physical layout that's generated can be pushed across to the 3D EM tool and simulated there automatically with those S-parametre files brought back directly into the circuit schematic and included in your simulation results. So let's move on then. Now you know the background to the tools. How do Modelithics libraries and Cadence AWR software work side by side? It really is simply a case of start the software and file new with library. That gives us access to all of the complete library that Chris defined for both active and passive devices. In some cases, you may pay to have access to specific vendor foundry items. For example, some of the amplifier devices have their own libraries that are available through Modelithics. And for the 3D EM components, we'll talk separately about the access to those from Clarity. So let's explore how these models are accessing the software itself, and please follow me as we go. Now, just as I'm starting up the software, I'd like to remind you all of the questions and answer button in the Zoom meeting that we're in today. If you have questions either for Chris for the first half of the presentation or for me as we go, please let me know and we'll cover those. So first, what I'd like to hope you can see now is the filter that Chris described. So in the circuit schematic diagram that we have on the top left corner here, we've come to the elements tree and we've brought in new with library, and we're loading the Modelithics library. In fact, what I'll do is I'll start a fresh design and we'll do that from scratch. So you can see that operating as we go. Just one moment and I'll find the right version of AWR because I have several on my machine. So let's start that up. This is actually the example that I'm going to show you in a few moments, the filter, but I wanted to start from scratch so you have a chance to see exactly how to load these libraries. And when we come to the file new with library, we have the option to bring in the Modelithics library. And as I've mentioned, some of the manufacturer's devices are slightly separate. What that does is that gives us the ability inside the software tool to start a new circuit schematic. And with that circuit schematic diagram from the elements world, not bring in the ideal capacitor that, as Chris alluded to, often gives close but sometimes inaccurate answers. There are no strays, no links to the substrate manufacturer's data, but instead we come down to the XML libraries further down, come down to the Modelithics library that I've just loaded, and either parts by type, where we can see the list of capacitor vendors, for example, or the amplifier vendors, or parts by my vendor name itself. What I'm going to do is come into the AVX component list, and from the 0201, drag in one of their components. You'll see immediately the component itself has a lot more data associated with it, including the pad level design and where that pad operates. The idea of whether it's a full simulation mode with the parasitics included or excluded for the EM simulation. And when I spoke about the single database, that concept idea is the fact that we have the 2D physical layout, but also the 3D layout of that chip component already provided for us in the design suite. Along with that model, not only do we need the electrical model, but of course we need the simulation substrate that accompanies that in order for that model to be accurate. So I'm suggesting we no longer use the ideal lumped elements for circuit simulation, but instead rely on the Modelithics libraries, the advanced RF and microwave library components, where we include information on the pads, and that's all dynamic and scalable. Perhaps if I took this up to double the size, you'd see the pads stretch in both the width and the height. And that's all something that ripples through to the 2D view and the 3D layout view. It's not layout versus schematics synchronization. So that was a passive component. If we come into the amplifiers and perhaps find one of the mini circuit devices, again, a huge library of parts. I'll just grab the first one here. As we drop that down, immediately you see the footprint for that amplifier placed into our 2D and 3D view. We simply connect to the input and output of that device. And this is the manufacturer's recommended footprint, copper grounding and heat sinking requirements, and the ability to connect in and out of the device. So once again, just to remind you, file new with library, we'd start with the Modelithics library. That process kit is shown loaded here, and we can come down to the Elements tab. And at the Elements tab, we come to the XML library folder and into the Modelithics library itself. Let's jump back to the slides. Now, they can be passive or active devices, and they're available to you. And as you saw on Chris's slides, even the same capacitor component can give very different simulation results dependent upon the substrate or perhaps even the bond pads that are required. We'll jump to the 3D models in a few slides, but that can also bring in a 3D package, and you get the response in the Clarity tool that I'll use shortly. In order to be complete as a slide deck when we send this out to those of you that are watching and those that have registered, I have a slide here, File New with Library to start a design. Now that's okay when you're starting a brand new design, but if you're midway through, for example, a filter simulation, and you want to add Modelithic libraries later on, you can certainly do that. Under the pull-down menu for Project Add Remove Library, you're able to add it partway through a design, and that will bring in the library list of components from Modelithics. And once again, you browse to the Elements XML folder and the Modelithics libraries themselves. So a slide there just to help you complete this if you wish to do this after the webinar. So the live demonstration itself for three designs that Chris alluded to. Let's start with application note 66. This was the filter design that he showed using passive devices from Modelithics. You now understand that the associated layout is generated automatically from the simulation schematic, and we'll jump into that as a filter design. The electrical items, as you saw a moment ago, come from the libraries, Modelithics libraries, and you'll see them throughout this filter design as being the inductors and shunt capacitors and other things used in this design. Of course, they all rely upon the substrate definition that this design is sitting upon. It's a 3.9 permittivity material from Rogers 4350 B1. The results, as Chris alluded to, when we simulate, yes, we have two measurement data files in this project. They've been imported as S-parametre data files, and you can see them just here. They've come from measurement equipment external to the software and been bought in, and we can plot those immediately on the software itself as measurement data files. But when we look to compare those with the results from the simulation, just as Chris showed you on the screen, we have the solid blue trace and the solid red traces very nicely following that measurement data, not just in return loss ripple, as you can see, but also in the ability to look at the insertion loss through the passband and even down to beyond minus 60 dB isolation out of band. They're following a very nice trajectory curve just here. Now we can go one step further forward than that with the microwave office tool. I spoke about the Axiom planar simulator. And what we simply do is in the schematic diagram, we have an extract block that links any of the passive topology. That's the transmission lines and the via holes and the substrate material that gets sent out. Anything you see here red in the diagram gets sent out directly to our EM solver. That EM solver would mesh the elements that you see, send that to a planar method and at moment solver tool to simulate this. And that will pick up stray coupling, not just with the components, but also with any of the via holes that interact, perhaps through the board structure or to edges of board material or between tracks. So not only are the advanced models incredibly powerful, when you bring in that automatic EM extraction, we get incredible agreement between insertion loss and match. There is certainly no need to design electrical designs like this filter off frequency just in order to compensate for inaccuracies in simulation software. Simulation tools today should be exact. Having spoken there about the passive design, let's look now at an active design. That active design includes the diode. Again, this is application note 85. It's the one that Chris spoke about in his slide deck earlier on. Only I'm going to open in the software, and again, you can see the results here having simulated working now with an active device. And the diode sits down here. Again, it's a Modelithics diode that comes from the library. We've dragged and dropped. It relies and is dependent upon the substrate. And if we go into the help files, those help files, just as Chris alluded to, take you directly to the Modelithics help pages, how the device is packaged and the pad sizes that go with, and the accuracy of the modeled versus simulated data as has been used to generate this electrical model. So a non-linear model that we drop into our design tool, the associated layout that is generated in the 2D and 3D views. And when simulating this, just as Chris alluded to, over three different simulation voltages, 0, 6, and 16 volts, you can see the accuracy on the solid blue traces here, tracing and emulating the measured data in the dotted black traces. Even quite a long way out of band. Appreciate they're not following exactly the depth of these traces here, but below minus 50 dBs is incredibly high accuracy for this type of filter design out of band, and they're following the correct trajectory and shapes. Return loss in band, once again, exact frequencies for the measured data and the simulation results. Now, of course, we've got a little bit more simulation data accuracy in terms of number of points here. So you'll see a slightly lower notch in simulation versus the measurement data files. So once again, very accurate on nonlinear designs. And to complete 3 examples, the slide deck here is talking about application note 99, I believe. This is a broadband detector. Once again, we'll drop into the software and just have a look at where that comes from. Once again, I've started file new with library and used the library components under the Modelithics, grabbing a part by type and specifically a diode. And from those diodes, we've dropped in a broadband detector diode here from the manufacturers. And in this case, it's a Skyworks Schottky diode, SKD, SKY, SC79002 that's been used in this design. Once again, remember it refers to the substrate material. So the schematic diagram has a substrate that we're using in this particular example. The layout is generated automatically. We could take that once again to the EM simulator, but no need here because the electrical models are fairly accurate, given that there is very little coupling along the length of this design. And when we look at the simulation results against measured data, from DC to 4 gigahertz, again following both this resonance very accurately. Simulated data is in red, measured data is in black, not just across the return loss, but also when we look at the voltage out of the diode device itself, at the high end, 2.5 gigahertz, but also at the low end at 915 megahertz. Incredibly accurate representation and right first time design from simulation tools, Microwave Office, when we use the correct electrical models provided by the Modelithics team. So back to a final slide from myself. We spoke a bit about the encrypted 3D packages from Modelithics, a separate library to the simulation models for electrical circuit simulation. But these come across and are encrypted. We load them directly into Clarity. Clarity is our 3D FEM solver. It comes from Cadence as a 3D FEM tool. And we simply start that software under the modeler, import a component, and the large list of component vendors is offered here once you install the Modelithics 3D component library. And we simply click to bring in that encrypted model as a 3D component, of which we can then have the correct dielectric material, the XYZ dimensions, the metallization, and all of the physical XYZ positions for bond wire transitions to come from a microwave office design out into a true 3D package. Now that could be a simple package like this, and apologies, it will drop the next component right on top. But if you were looking at an amplifier design and having an amplifier package, perhaps from mini circuits, you end up with the full package of the mini circuits device, just as you saw earlier on, come in, and we can connect to that in the 3D world and bring that back into microwave office to use as a design package. Now, I appreciate in the training today, this webinar, we've spoken a lot about how to drive the software. There is a lot of customers around the world that are using our free online training or training bite videos. Once again, like the earlier instruction slide, I'll leave this in the slide deck pack that will be shared with you within about a week of this webinar. And the QR codes here are live and dynamic and up to date, and you'll be able to get access to some of that free training online at cadence.com/training. So with that, a quick summary from my half of the presentation. Remember to start a project if you know you're going to be designing with the Modelithics components, file new with library to begin with. If you are partway through a design, for example, a filter, that you want to move from ideal components to realistic active or passive devices from the Modelithics libraries, we can use project add remove library. For the 3D component packaged elements, these are encrypted. And Clarity 3D FEM Solver is the tool that we need to read those encrypted libraries into. That allows us to design and bring that data in and export that back into microwave office. And finally, perhaps to preempt one of the questions that might come, if there's not a component part available in the Modelithics XML library folder, at the top level, there is a link that you can jump into straight away. And again, let's show you this. At the top of the library list, there is a Modelithics I need a model. We simply right click here for an active. We right click here for a passive element. It will open you up a web page where as a customer, you can define the part that you're looking for from a specific vendor and request that to the Modelithics team. And we go forward and generate a library element for that moving forward to the future component libraries. So I hope that's been a good introduction to the tools and how to use those elements inside the software itself. Thank you all. Bye-bye.